Hello friends, welcome back. Welcome to Pebbles SSC. Now let us see the next topic of the first chapter of geometry, similarity, and that is areas of similar triangles. Now we have already studied that if two triangles are in the ratio, then the ratio of their areas is equal to the ratio of product of their base and height. For example, if two triangles are similar to each other, then the area of triangle 1 upon area of triangle 2 is equal to base of triangle 1 into height of triangle 1 upon base of triangle 2 into height of triangle 2. This is what we have already studied. Okay. Now let us see what is the relation of the sides of the triangle to its height. Okay. For example, if these two triangles are similar to each other, okay, so this is their height. You know that their height is the perpendicular to the base. Okay. Now suppose this is, I'll call it as a ABC and I will call it as PQR, and let us these be X and Y. Now we know that these two triangles are similar triangles. That means this angle is equal to this angle, correct? Now we will consider only half of the triangle, not exactly half, but of one part of the triangle, right side part of the both the triangles. So now let us consider the triangle CXB and RYQ. We know that angle B and angle Q are equal, congruent angles, and angle X and angle Y, that is RYQ and CXB, are right angle triangles. So by the AA test of similarity, these two triangles are similar triangles, and hence you can say that CB upon RQ is equal to CX upon RY. So we can also say that here we can say that the sides of first triangle, any side of the first triangle or the corresponding side of the first triangle, is equal to H1 upon H2. So this is my H1 and this is my H2. In short, we want to say that whenever two triangles are similar to each other, their sides are in proportions, but their heights are also in proportion with their sides. Okay, let us go ahead. The theorem says that the ratio of areas of similar triangle is equal to the ratio of squares of the sides or the square of the corresponding sides. For example, if ABC, triangle ABC is similar to triangle PQR, then the area of triangle ABC upon area of triangle PQR is equal to the ratio of square of the corresponding sides, that is AB square upon PQ square is equal to BC square upon QR square is equal to AC square upon PR square. This is the theorem. Now based on this, I can also say, like we proved that the sides, ratio of the side is equal to the ratio of heights. Now let me show you one thing, that this is, suppose ABC and this is triangle PQR. Now suppose this is the median M, and for this is the N. Suppose AM and PN are the median, then I can also say that this ratio of area is equal to AM square upon Pn square. That is, it is also equal to the area, ratio of the area is also equal to the ratio of squares of their medians also. You remember we just shown that the side, ratio of side equal to the ratio of the heights. So similarly here also we can prove that the medians, the square of the medians is, that ratio is also equal to the ratio of their areas. Furthermore, we can also show that this is equal to perimeter square of 1 upon perimeter square of second triangle. Now showing perimeter is very easy because we know that AB upon PQ is equal to BC upon QR is equal to AC upon PR is equal to K. Now we can easily show that by a theorem on equal ratios, AB plus BC plus AC upon PQ plus QR plus PR is equal to K, and hence this is nothing but this addition is nothing but the perimeter of triangle 1, and on the denominator it is the perimeter of the triangle 2. So you have to remember this. This is the ratio of areas of similar triangles, and we have to solve the examples based on this. Now I have already told you that similarity is a very easy chapter to understand and even to solve. But the only thing is, in the similarity you don't have to only deal with similarity. So many other things are there. You have to use your past knowledge up to 9th standard in solving this. Okay, so let us see few solved examples on the areas of similar triangles. The examples are extremely simple. Let us solve few examples and then we will go to exercise 1.4. Okay, so let us solve few examples. Now as I told you that the examples are very simple, but remember in the examples of similarity chapter many times they don't give figure. Okay, only the word problem is given and you have to draw the figure. So draw figures very carefully, and even if you think that the example is very simple, still draw the figure. Okay, don't try to avoid drawing figures in any problem of your geometry. Figure is given, then you will definitely draw it, but if it is not given, still you have to draw the figure, because once you draw the figure you make sure that everything is given comes in that figure. Or if you just try to solve it without figure, what will happen? Sometimes you may miss something from what is given. Okay, so let us see a few examples. The first example is the triangle DEF is similar to triangle MNK. The first example, DEF is similar to MNK. I am not drawing the triangle. Okay, anyway, you have to draw the triangle there. If DE is equal to phi, first of all we will draw two triangles, because I told you to draw figures, so I will draw two triangles. DEF and MNK. They are given. See, this example is extremely simple. I am just showing you because this is the first example I am showing you. Okay, otherwise nothing great in this example. Okay, DE is 5. DE they are given 5. Then MN is 6. MN is 6. Then find a value of area of DEF upon area of MNK. I told you this is very simple example. Find area of DEF upon area of triangle MNK. This is what we have to find out. Now as I told you that example is extremely simple, still I have drawn the figure. So this is advice to you that don't try to avoid the figures even in case of such a simple example. Okay, because it's a habit. If you develop this habit of drawing the figures, then you will never miss any example, any given from the papers. Okay, so I don't think I should solve this, because we know that a ratio of area of triangle is equal to ratio of square of the sides. So this is nothing but equal to 5 square upon 6 square, 25 upon 36. Very simple example. Actually I should not have shown this, but still such a simple example don't expect to come in your papers. Let us go ahead and solve next example. Second example, if triangle ABC and triangle DEF such that the area of triangle ABC is 9 centimeters square, area of triangle ABC is equal to 9 centimeters square, and area of DEF is 16 centimeters square, area of triangle DEF is 16 centimeters square. If BC is 2.1 centimeter, find the length of EF. If BC is 2.1, BC is 2.1 centimeter, then find EF. Extremely simple example. First, draw the figure, even if it is not required. Here we know that these two triangles are similar triangles. So BC is corresponding to EF. Okay, so what our theorem says? The ratio of their areas, this ratio is equal to square of this, that is 2.1 square upon EF square, isn't it? So now you have to only solve this. 9 upon 16 is equal to 2.1 square upon EF square. So you have to find a value of EF. So I hope you can do it. So please pause your video right now and first draw the figure, even if it is not required, and then write that the area of triangle ABC upon area of triangle DEF is equal to BC square upon EF square, dash from theorem. Okay, then 9 upon 16 is equal to 2.1 square upon EF square, and then find the value of EF. So please pause your video and solve this. I hope you have solved it. Okay, the answer is 2.8, but I'm sure many of you while solving this must have done like this. 9 upon 16 is equal to 2.1 square upon EF square. So I have seen in the papers or in the notebooks of the students, they first square this 2.1 square, that is 2.1 into 2.1. But whenever you come across such kind of ratios or any kind of the numerical example, that is, this is the arithmetics. Okay, so first watch it carefully. Can you see that both are the squares here, and here also both are the perfect squares, 3 square and 4 square. So you can first take a square root of the both the sides. So it will be 3 by 4 is equal to 2.1 by EF. Okay, I just shown you this because I came across many papers where the students have first 2.1 into 2.1, then they did all the calculations, and then they try to took the square root of the EF. That is wrong. So be careful. This is how you are going to be expert in the arithmetics. Okay, watch carefully first. Don't immediately go on solving. First watch carefully how easy can you solve this particular example or these particular steps. Okay, let us go to next example. Third example, the figure is given something like this, where the angle B and angle A are perpendicular angles or the right angles. PO is given 5, OQ is given 7. Now let us read the example. in this figure, segment PB and QR are perpendicular to AB. PB and QA are perpendicular to AB. If PO is 5 and QO is 7, 5 and 7, and area of triangle POB, area of triangle POB is equal to 150 centimeters square. Area of triangle of POB is given 150 centimeters square. We have to find out the area of triangle QOA. QOA, this triangle area we have to find out. Now by looking at this example, many students make one mistake here. They consider that these are the similar triangles because they have that theorem in their mind, that is the area, ratio of the area is equal to ratio of squares of the sides, and they immediately write down area of triangle POB upon area of triangle OAQ is equal to PO square upon OQ square, and they solve it, they find the answer perfect. Okay, answer is also correct. The answer is 294 centimeters square. Answer is also correct, but they will lose majority of the mark. For example, if this sum is for the 3 marks, they will get only 1 mark. Why? Because you have not read the problem carefully. Nowhere in the problem they are given these two triangles are similar triangles. You have to first prove that those are similar triangles, and only after that you can apply the theorem, because theorem is for areas of similar triangles, not any two triangles. Okay, now proving that these two triangles are similar is very easy. How? These two are vertically opposite angles and these two are the right angles. So by AA test of similarity, these two triangles are similar triangles. So triangle POB is similar to your triangle QOA. First prove this and then solve the example. Okay, so the rest of the example is very easy. 150 upon that area is equal to 5 square upon 7 square. The answer is 294. Problem is very easy. Please pause your video here and solve this problem. Now, example number 4. Figure is given. This is an interesting example. What they say that ABC is a right angle triangle. Now they have drawn the equilateral triangle to the each side of this right angle triangle. That means AC is the base and this is equilateral triangle, this is equilateral triangle, and this is equilateral triangle. And what they want to prove that PAB plus RCB, area of triangle PAB plus area of triangle RCB is equal to area of triangle QAC. That means we have to prove that area of this triangle plus area of this triangle is equal to area of this triangle. This is very easy. First of all, let us consider these two triangles, then we'll consider these two triangles, and then we will add. Now for when these triangles are equilateral triangles, that means those are equiangular also. You know that for the extra information, any equilateral triangle, the internal angles are 60 degrees. So since these two triangles are equiangular triangles, so we know that in triangle PAB is similar to triangle QAC. And what will be the areas of their ratios? So area of PAB upon area QAC is equal to sides, ratio of their square of the sides, AB square upon AC square. AB square upon AC square. And similarly we can write that RCB is similar to triangle QAC. So here I can say that area of RCB upon, I am not writing a triangle sign there, but you have to write triangle sign also. QAC is equal to what we can say that BC square upon AC square. Now we can add, this is my first statement, this is my second statement. When I add these two statements, what will happen? Now I will add these two sides, area of PAB upon area of QAC plus area of RCB upon area of QAC is equal to AB square plus BC square upon AC square plus AC square plus BC square upon AC square. Now here QAC is a LCM, so I can write area of PAB plus area of RCB upon area of QAC is equal to AB square plus BC square upon AC square. Now what is AB square plus BC square? AB square plus BC square, we know that by Pythagoras theorem, we know that it is nothing but AC square, right? So here I can write AB square plus BC square is equal to AC square upon AC square, that is equal to 1. So AB square plus BC square is AC square upon AC square, so AC square upon AC square, which is nothing but equal to 1. And so we have area of PAB plus area of RCB upon area of QAC equal to 1. Just take this QAC that side. And so you will get PAB means area of PAB plus area of RCB is equal to area of QAC. Simple. So please pause your video here and complete the last step. Next example, example fifth one. Two triangles are given. These two are the isosceles triangles. Let us read the example. Two isosceles triangles, isosceles means two sides are equal, okay? Two isosceles triangles have equal vertical angles. These vertical angles are equal. A and D, angle A and angle D are equal. And their areas are in ratio 16 into 25. Now, if I call this 1 and 2, then area of 1 upon area of 2 is 16 upon 25. This is what given is. Find the ratio of their corresponding heights. Corresponding heights ratio. We know that by the theorem that the ratio of areas of similar triangle is equal to the ratio of squares of their corresponding sides, maybe corresponding medians, corresponding altitudes, corresponding perimeters. All these three things are there. So here this ratio can also be equal to the corresponding heights. We have to find a ratio of corresponding heights. So this is nothing but h1 upon h2. But when these two triangles are similar triangles. Till now they have not stated that these two triangles are similar triangles. What they have stated? They only said that these two are the isosceles triangles where angle A and angle D are equal. So first of all, let us prove that these two are similar triangles, and then we can say by the property 16 upon 25 is equal to h1 upon h2. Okay? Sorry, this is h1 square upon h2 square. Okay, so let us first try to prove that these two are similar triangles. Okay, now here I can say that AB is equal to AC. Why? Because isosceles triangle, and here DE is equal to DF. So what is AB upon AC is equal to 1, and DE upon DF is equal to also 1. So these two are 1. So I can say that AB upon AC is equal to DE upon DF. Correct? Now I'll just interchange, and hence AB upon DE is equal to AC upon DF. So AB upon DE is equal to AC upon DF, and this angle are congruent angles. Top angles they are given as a congruent angle, A and D. So by SAS test of similarity, these two triangles are similar triangles, and hence the ratio of area of similar triangle is equal to ratio of square of their heights, altitudes. So now I can say that H1 upon H2, I am taking square root of both, 4 upon 5. So the answer is 4 upon 5. The ratio of their heights is 4 upon 5. So please pause your video and first complete this example in writing. Okay. Now whenever I am solving the example or I am explaining the examples here, you have to listen very carefully. Why? Because I am not spoon feeding you. Okay, I am not writing for each and every step. I am not writing the reason for that, but you have to write the reason. Okay, sometime while writing the names of the triangles, I don't write that triangle sign, that is area of triangle ABC. I just write area of ABC, but you should not write like that. That is why I always say that pause your video and solve this particular example completely in all respect. Okay, so don't forget that I'm just telling you the reasons, but you have to write the reasons also. Okay, so please pause your video here, complete this example, and then we can move to exercise 1.4. Thank you very much.